We know from the momentum unit that momentum is conserved when there are no net external forces on the system. So if we have a situation where we have a block colliding with another block, then there are forces that are acting between the two blocks, but there's no forces pushing on it from the outside. There's no net external forces. So in this particular situation, momentum would be conserved. But energy is conserved when there are no losses to heat. So what are the different names for these types of energy collisions? Well, the first one is called an elastic collision. An elastic collision, you can think of the word as elastic as sort of like bouncing. That says that the total energy that we start with is equal to the total energy that we end with when we're dealing with mechanical energy. In other words, another way to say that is there's no heat lost. So in an elastic collision, we're allowed to say all of the energy we start with equals all the energy that we finish with. But when we're talking about an inelastic collision, then we would say that the mechanical energy does not add up because we have losses to heat. And usually in the problem, they're going to say this is an elastic or this is an inelastic problem. So let's do one of these problems. This one is inelastic, but there's no net external forces. So that means momentum is conserved here, but energy is not. So we want to find the heat produced, and we can't use the kinetic energy. We can't say 1/2 mv squared equals 1/2 mv squared over on this side because they're not equal. But we can use conservation of momentum to find the velocity, then find the new kinetic energy, which will be less than this kinetic energy here. So let's go ahead and do it. So we're going to use conservation of momentum. So we're going to say all the momentum initial equals all the momentum final. And that's going to be m1 v1 equals m1 plus m2 times our new velocity we'll call v prime. And then we just put in our numbers. We have 2 and 2 equals 2 plus 1 times v prime, or we can say that v equals 1.33 meters per second. Now we can do conservation of energy because we know the velocity after the collision. So we say all of the energy that we start with equals all the energy that we end with. So we start with 1/2 mv squared of the first block, that's the first block, equals 1/2 mv squared after, and that's going to be the mass of the two blocks plus q. So what's the start of the problem? We have 1/2 2 times 2 squared, and that's going to be equal to 1/2 m1 plus m2, so that's going to be 3 times the 1.33 that we figured out from conservation of momentum plus q. So this energy that we have here, which is 4 joules, is going to be more than the energy after the collision, and I don't know what the math is on that, but when you add all of it up together, you end up with Q, the leftover energy, being 1.3 joules, or you can think of it as the missing energy. This problem is called the ballistic pendulum, and it was originally used as a way to find the speed of a bullet before they had electric timing methods. So the way this problem works is we have a bullet cruising along at some unknown velocity, and it embeds itself in a block, and then the block and the bullet together swing up into this new position with a height h. So the way that we're going to do this is, well, look at the way we can't do this. We can't say the kinetic energy of the bullet here equals the potential energy of the bullet and block system here. Because heat is lost during this collision, it's going to embed itself in there. There's going to be some kinetic friction as the bullet slows down, and that is going to produce heat. So we're going to break this up into two phases. We're going to do phase one, conservation of momentum. Now listen carefully to this part. This is going to be the collision of the bullet with the block, and then we're going to find the velocity of the block bullet system the moment after the collision ends, but before it moves up. Okay, so the first part is the conservation momentum of the bullet and the block. Then that's going to get us the velocity so we can figure out the kinetic energy of the bullet block. And then that energy, that KE, is equal to this because energy is conserved after the collision. Energy is not conserved before the collision or during the collision, only after. So to be able to do that, we are going to start out with a conservation of momentum equation. So that's going to be, we can think of it as m1v1 equals m1 plus the larger m2, that would be the block, times the new velocity v2. And that's going to be the velocity the instant after the collision, but before the rise. Okay, so they gave us the mass, so that's going to be 0.0095 times our initial velocity, v1, equals the mass of the block plus the mass of the bullet. Now, if you don't put that in there, you'll probably get the same answer, but if you don't do that on a test, you're going to lose points. And that's equal to v2. So here we've got a problem. We have one equation with two unknowns. So what we're going to do is we're going to isolate for v2, and when you do the math on that, you get 0.00176 v1. So now we have v2 in terms of v1. This velocity is the velocity after the collision, but before the rise. So now we can do conservation of energy. So conservation of energy tells us that we have the kinetic energy right after the collision is going to turn into the potential energy of the system when it rises up. So that's going to be 1/2 m1 plus m2, because remember this is the bullet and block together, equals v squared, and that's going to be v2. And that's going to be equal to m1 plus m2 times g times h. Since this is the bullet and the block, and the bullet and the block rise, we can get rid of these. So that leaves us with 1/2 v2 squared equals gh. And all we need to do is multiply through by 2 and sub in for v2. So that's going to be 0.00176 v1 and all of that squared. And that's going to be equal to 2gh. And putting in 9.8 for this, and the height that we were given of 6.3 centimeters. So I'm not going to put those numbers in. I'll just tell you, if you want to work it out yourself, you can. That V1 comes out to 631 meters per second. And that is if you put in 9.8 here, and you put in 0.063 meters for h. This is a cool problem that has a lot going on with it. And to start this out, I'll just kind of go over the whole thing. We have a 2 kilogram block that is dropped onto an uncompressed spring. It falls for 0.2 meters, so it gains speed, then it hits the spring, and the spring is going to compress. Now, the amount that the spring is going to compress here is going to actually be double the distance to the equilibrium point. So if we want to look at the different forces that are involved, this will help us to understand what's happening while this block is colliding with the spring. And I didn't mention it, but what we're looking for is the maximum velocity. When does that occur, and what is it? Okay, so while the block is falling, there's the force of gravity. That's easy. There's no other forces acting on it other than gravity, so it's accelerating at 9.8. Then the spring starts to scrunch up, which means that the force that the spring is exerting up is actually less than the force of gravity down. Now, why is that the case? Let's look at equilibrium. So if we just took the block and just set it on the spring, this is how much it would scrunch up. So that occurs at equilibrium when these are equal. So if the scrunch up is less, at this point, Fs is less. Now this is important because the acceleration during the fall is 9.8 meters per second squared. But in this situation, when the spring starts to scrunch up, there's still a net force down, which means that even though it's getting the spring's pushing on it, it's still speeding up. And it's going to speed up until the point where the net force on it is 0. So it's kind of counterintuitive. When there's no force on it, that's when the velocity is going to become maximum. Then what happens when it starts to scrunch up more than that? Well, the force of gravity is the same, and at that point, the force of the spring is more, meaning there's a net force up. And if there's a net force up, that means there's going to be upward acceleration. So the block speeds up, continues to speed up, but at a lower and lower rate. So it's speeding up, but not as quickly, until it reaches its maximum velocity, and then it slows down to the maximum compression down here. So let's go and solve for Vmax. How do we do that? Okay, so we know that we're going to start doing this at equilibrium. At equilibrium, we're going to say that PEG equals PES plus KE. Okay, so this is going to be the potential energy when we have the block at the point at which the spring potential is going to be from equilibrium, whatever that distance is that we don't know, and at its maximum kinetic energy. So at equilibrium, we know that Fs, the force of the spring, is equal to Fg. So we can just put in Kx equals mg, and the spring constant, I didn't mention this above, the spring constant's 50 newtons per meter, and we don't know the amount the spring will be stretched, and that's 2 times 9.8. So x comes out to 0.392 meters. Let's go ahead and look at this. So I should have said K equals 50 newtons per meter. That's a given in this problem. So when it's at equilibrium, we did the force of spring equals force of gravity, and we figured out that X is equal to 0.392 meters. That's also going to be the maximum compression down here. So now that we know the compression, what we can do is say that we know the PEG, and that's going to be the distance from here down to here. So that's going to be 0.2 plus 0.392. And the amount the spring is compressed, X, is going to be 0.392. So let's go ahead and do that. So we can say PEG equals PES equals KE. And that's going to be mgh equals 1/2 kx squared plus 1/2 mv squared. So we know the mass of the block, that's 2, gravity's 9.8. And now what is height? Height is 0.2 plus 0.392. And that's going to be equal 1/2 50 times the amount the spring got scrunched up, 0.392 squared, plus 1/2 times 2v squared. And if you work out the math on that, you get 2.8 meters per second, and that's our maximum velocity. So I thought it would be good to sort of go over this and look at the graph. So during the first 0.2 meters of fall, this is accelerating at 9.8 meters per second squared. It's just falling. Then it comes in contact with the spring, and the velocity is still going up. The velocity is going up, but the rate at which it's going up is decreasing until it gets to this point. Its maximum velocity is 2.8 meters per second, but the slope of this line is 0. So the maximum velocity occurs when the acceleration is 0. And this concept is going to come up again and again. And then what happens? The slope becomes negative, meaning the acceleration is in the opposite direction, and the velocity is decreasing until it gets back to the original point. This problem's pretty different from the other ones, but it is a conservation of energy problem, or actually it's a work into energy problem, but it starts to involve some concepts that we're going to see more frequently come up in the next unit, which is center of mass, because there's a shortcut way to do this. But if you're asked to do this as an integration, I'm going to show you how to do it. Okay, so here's the problem. You have a chain of length L, and it's hanging over this table edge, and you grab onto it and you pull it up onto the table. So the question is, find the work to slide this up onto the table. There's going to be no friction in this, so we don't have to deal with that. But you can see that there's a problem. And that problem is that the force is not constant. As we drag this up, the amount of chain that's hanging over the edge decreases, so the force of gravity decreases. And that should be a hint that we're going to need to use an integral. So we're going to see this again in center of mass, but we're going to use the idea of density, or more specifically, mass per unit length. So let's say we have a length of chain like this. We know that the mass per unit length is kind of the idea of density, where this is a constant. If we cut this in half, we would have half the mass and half the length, but the ratio of mass to length would be the same. So we could say that m over L is a constant. So what we're going to do is let's look at a little tiny chunk. So that we could do this integral, we want to do this for little chunks that we're going to lift up. And the mass of that little tiny chunk would be the derivative of m, dm. And the thickness of this we can call dx. So the ratio of dm divided by dx is the same as the whole mass divided by the whole length. So we can say dm over dx is equal to m over L. And that way we can find dm, which is going to be m over L dx. So what is the weight of the hanging segment? Like, how much does it weigh, the part that's hanging over the edge? Remember, that's changing. But we want to be able to write that in some expression, and we would say it's Fg equals mg, but remember that m is changing. So what we can do is we can say density equals m over L. So we can rearrange that, and this concept, again, is the letter rho. It just means the mass per unit length. We can rewrite that as m equals rho L, and then we can say m, and that's going to be the mass of the chain that's hanging, is going to be equal to m of the whole chain divided by L times the amount of chain that's hanging over the edge. that's going to be our L that's hanging over the edge. So in that case, that's going to be our delta xy, this part right here. So to be able to do that, we can now say that we know the mass hanging over the edge is m over L delta xy. So we can just put that in and say Fg is equal to m. And what is that m? It's m over L delta xy times g. I'm just going to rearrange that and say mg delta xy over, make that look more like an x, over L. So now we know that the change in potential energy is equal to negative F dx. And because the amount of chain that's hanging over the edge is 1/4 the length, we are going to be integrating from what to what? Well, that's going to be from negative L over 4 until it's on the table at 0, because we're calling 0 height the table. So if we wanted to write this out, we could say delta U equals negative the integral of minus L over 4 to 0. And that's going to be our force. And what's our force? We just figured it out. It's mg delta xy over L dx. We know that mg over L, mg, and L are all constants. So we can just say mg over L, the integral of delta xy dx from L minus 4 to 0. And we know the integral of x dx, that's x squared over 2. So we end up with minus mg delta xy squared over 2L from minus L over 4 to 0. So now all we have to do is put in our numbers. So that's going to be 0 minus a minus 0.012 times 9.8 times the length of the chain, which is 0.28, and that's over 4. And that's squared, and that's all over 2 times 0.28, and we end up with a change in potential energy of 0.00103 joules.